Hey, y'all. You guys hear me? Should probably go to the first slide. There we go. Hello? Anyone there? Or is my mic just not working? All right, awesome, cool. Hola a ti también. So 6 people in the stream right now. All right. Yeah, I think we can get started because there's a surprising amount of people that are first here. We'll wait a little bit, actually. How was your guys' week been? Anything bad? Anything good? Any crazy stories? I love a crazy story. All right. So we can go ahead and get started. Since there's people on the stream already. Just not normal. It takes a while to flood in sometimes. So the first thing is, if you want to get alerted on more streams, follow 5 of them on social media, especially prevalent on Instagram. Recently, they've been posting like every stream that happens in a night on the Instagram story the day of, and that's really helpful, honestly. So yeah, follow if you want notifications. I think that's the best part. And there's also, you get free resources or alerted about really good resources besides Fiveable, which is nice. Or just Fiveable resources in general. So today we're going to be reviewing atomic structure because it's really relevant to resonance. We're going to be reviewing stability because stability is the reason why resonance happens. Then we'll be defining resonance after that, and talk about resonance structures. And when we're talking about resonance structures, the formal charge part is below resonance structures, like it's a separate category, but they're really one and one together. And then we're going to talk about the applications of resonance to acids and bases. And if you don't know what an acid and base is, we can talk about it then. But for now, that's just a little side piece. So we're going to be reviewing structure. And the first part of structure that we're going to have to review is electronegativity. And electronegativity is just the tendency to pull electrons in, right? So if we have a periodic table here that shows the electronegativity trend. Fluoride being, according to the trend, the most electronegative, and francium being the least electronegative. This is because fluorine is very close to the noble gases. So it's an atom's goal is to get 8 valence electrons in its shell. So fluorine is very close to that. And it's also the smallest of the groups that are closest to that, right? Because chlorine and fluorine are just as close to getting that full shell, but fluorine's smaller, so the force on that electron that is pulling it is greater, just because there's less electron shielding. And the same case goes for the other trend, the up and down trend, and side to side trend, all that good stuff. So the example here I have is hydroxide. There is an electronegativity difference. The electronegativity of oxygen is 3.5. Electronegativity of hydrogen is 2.1. So the oxygen in the hydroxide ion has greater electronegativity. So the electrons in that bond are going to move closer to oxygen. So that leads us to polarity. And big electronegativity difference leads to a polar molecule. Polar meaning implying molecule has poles. Like when you hear someone talking about politics, they say politics are really polarized. That's because that means that they're really far apart. There's a big difference, a much bigger difference than there used to be. It's in that same case, a polar molecule has a much larger electronegativity difference than a nonpolar molecule does. And in this case, these poles mean charge. Poles can be really anything. If there's things that are separated by if there's 2 things that are very opposite to each other or different in intensity, and they're far apart, and that's poles. They have poles. So for example, here hydroxide has a polar push to it. Hydroxide is a polar molecule because the electronegativity difference is fairly large. 3.5 minus 2.1 is 1.4. That's a pretty big electronegativity difference. So when we talk about an uneven pole of electrons, that's called a dipole moment. And a dipole, di meaning 2, pole meaning pole, so it's dipoles so it's a dipole because it has two poles. And a moment means a product between a distance and another quantity. For example, if you know physics, you know a moment in physics is generally a force times a distance. But in this case, it's a separated charge by a distance. You don't have to know how to calculate dipole moments, but they are very important. And in terms of what a dipole moment actually does outside of chemistry, if you put a dipole in a magnetic field, it'll spin. So there's a dipole moment on hydroxide, and the dipole moment points towards the oxygen, and the dipole moment points in the same direction that electrons are being unevenly pulled. So that's a dipole moment. And because electrons are being pulled and pushed, they create positive and negative charges. So you know electrons are negatively charged, right? So if the electrons are being pulled towards one atom, that atom's going to have more negative charge than the one that's losing them. So there's an electron deficiency on the left side of that molecule right there. The hydrogen is getting an electron deficiency because the electrons are being pulled away from the hydrogen. So when that happens, the hydrogen gains a partial positive charge, which is what that curly letter there means with the plus. The curly letter, that's a Greek letter. It's a lowercase delta. You may know the uppercase delta, which is the triangle when you're talking about like change in a quantity, where like slope is like delta y over delta x, change in y over change in x. In this case, the lowercase delta means a small change, a small difference, and the positive just means positive. So there's a small positive, a partial positive on the hydrogen. There's a partial negative on the oxygen because the oxygen is slightly more negative because the electrons are being pulled more towards it. But for example, a molecule can have a polar bond but still be nonpolar. So for example, we have C2O right here. And the CO bond is polar because oxygen has a 3.5 electronegativity, carbon has a 2.5 electronegativity. So those are polar bonds. However, there's something called vector addition. It's just fancy words for the dipoles are going in opposite directions. So they're going in opposite directions and they're the same in strength, so they essentially cancel each other out. If you think like you have a, I'm trying to think. I have a piece of paper right here with my calc work. If I'm pulling on it on both sides, I'm pulling on it still and it's not ripping, but there's no total force on it because I'm pulling just as strong with one hand as the other one. So that's in the same case here. The electrons are being pulled towards the carbon, or they should be pointing towards the oxygen. That's my fault. But they're being pulled towards the oxygen in an equal way, so it cancels out. So the molecule itself is nonpolar. So the total dipole moment is just the sum of the dipole moments, but because one's moving in an opposite direction, it's negative. So when you're adding two things that are equal to each other, that's what that big funny looking E means. That means sum, you're adding them together. They add to zero because they're equal to each other, but they have opposite signs. So the next part of structure that we need to review is bonds. So suppose we want to break the carbon-carbon double bond in ethene. Which step of the process do you think will take more energy to complete? Step 1 or step 2? Just throw a guess out there if you don't know. And if you have a sheet of paper with you, it might help you to like draw out these processes in terms of like Lewis structures, because it'll be a little more obvious because this notation is kind of abstract. Come on, guys. We got 7 people in the stream. One of you can throw a guess out there. No, it's step 1. And the reason why is because there's these things called sigma bonds and pi bonds. And the pi bond is the second bond on the double bond, and the sigma bond is the first bond. If you think of like orbitals, the sigma bond holds the s orbital and the pi bond holds the p orbital. That's why they're named that way. But a sigma bond requires more energy to break than a pi bond, because when you're breaking that pi bond, that second bond on that double bond, you're not changing the shape of the molecule. You're not breaking this carbon-carbon double bond. You're simply moving the electrons around. So when you break the first pi bond, you're not doing anything more than moving electrons away. But when you break that sigma bond, you actually rip the molecule apart. So step 1 takes more energy to complete. Does that make sense, guys? Okay, awesome. So we just talked about sigma and pi bonds. So how many sigma bonds are in ethene, which is this molecule I have right here? Yeah, so there's 5 sigma bonds. You're mixing up the, Amelia, you're mixing up the letters there. The pi bond is the second bond on that double bond. So there's only 1 pi bond and 5 sigma. Yeah, the idea, right? It's just the terms of it's just a term of like vocab. So yeah, pi's the pi bond is the strongest bond. So yeah, so 1 pi bond, 5 sigma bond. How many of you like biology? Because if you don't like this stuff that much and you like biology, you might get a little comfort from the next slide I'm about to show you. You probably won't, but there's a chance. No bio fans in here? Sweet, me neither. Kidding. So the example I have here is the adenine thymine base pair in DNA. And my question is, I'll go with the first one that's easier. How many pi bonds do you guys think there are in this in the total base pair, not just in adenine or adenine or thymine, in both the molecules combined? How many pi bonds are there? You're Natalie, I think you're trying to count the sigma bonds. I said pi bonds. Asking how many sigma bonds there are is actually on the slide, but I'm not feeling as evil as I was when I was making these slides. So I'm not going to ask you to do that. There's 7 pi bonds. Yeah. If I know I counted the pi bonds right. If anyone wants to if anyone was feeling extra county today, you can count the sigma bonds and spit them out in the chat right now. But I don't think anyone likes counting that high. But yeah, so 7 pi bonds. And we're going to go over that. So, yeah, so 7 pi bonds, 30 sigma bonds. If I counted that right, I totally could have counted that wrong. And if that's the case, then I'm the idiot. So we're going to analyze this molecule a bit more in depth because although this is definitely a biology thing, DNA is rich in chemistry concepts. It better be rich and complex, or else we wouldn't really exist, which would be a problem. So we're going to analyze this a little bit. And the question that I have here is, why are they attracted to each other? I'm not asking you guys that, but we're gonna talk about it in terms of molecule polarity. So I'm gonna go ahead and switch to. Oh, I almost accidentally clicked the exit button on the tab. That would have been bad. Application window. Right. So I'll make the canvas a little bigger so we can actually do stuff with it. Okay, so that's the first thing. So we're going to talk about how many pi bonds there are. For first off, we're going to actually count them on the screen. So I'm going to cross them off in a new layer so it doesn't mess with the thing. There's 1 pi bond here, 1 pi bond here, 1 pi bond here, 1 pi bond here. That's 1, 2, 3, 4, 5, 6, 7. So 7 pi bonds. So we're going to count the sigma bonds now because that's fun, right? So it's essentially literally every single bond on here. These green lines right here aren't a chemical bond. That's just an electric attraction. But So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 30 sigma bonds. If you miscounted a little bit or you didn't count the bond to the R groups, honestly don't feel bad. This kind of stuff it's like really stupid to ask you to count big numbers without like this molecule on paper, because like just I clearly have the advantage because I was able to cross stuff out. So we're going to talk about the reason why this molecule stays together in like a DNA strand. So when we're talking about let's look at the NO bond here. So when we have an NO bond, so I'm gonna look at periodic table just to help me out a little bit. Periodic table. So when we talk about the NO bond, which one is more electronegative? Or that should be an NH bond, not an NO bond. That's my bad. When we talk about the NH bond, which one is electronegativity, the nitrogen or the hydrogen? Throw a guess out there if you don't know. Yeah, so the dipole moment goes this way, which means that this nitrogen has a partial negative charge and this hydrogen has a partial positive charge. And then when we talk about this interaction right here, the oxygen is also partially negative, but because this electronegativity difference is like so large, this hydrogen is very, very, very electron efficient. So it's very attracted to partial positive. It's very attracted to partial positive molecules. And this oxygen is partial positive right here. So if you literally just have like a positive charge, this is essentially a positive charge and a negative charge just next to each other, and they're going to attract. They attract very strongly because the nitrogen-hydrogen has such a strong electronegativity difference. Does that make sense? And it's the same case with the interaction on the bottom of the page. The nitrogen is partially negative by nature, and this becomes so partially positive because that electronegativity is the difference is just so large that there's a very strong attraction. And you don't have to know this in depth right now. This is called hydrogen bonding. And it is actually going to be, I think, either my next week's stream or the week after that, where I talk about hydrogen bonding, especially in biomolecules like this. We're going to go more in depth with this stuff. So yeah, one quick thing. Do you guys know like this notation with the dashed lines and the wedge on this carbon right here? If you don't, just let me know, because like it's very easy. Okay, so here, where's the CH3 that I could use as an example? All right, looks like I'm building a CH3. I'm using my model kit right now to do this, just because that's the easiest way to explain it. So we have still building this. Hold up. Almost done. So this is a CH3 right here. This is a methane. And when we look at the molecule, like for example, if we look at it in a plane like this, there's one molecule coming at you and one going behind you. So when we talk about this right here, this hydrogen is coming out of the page, and this hydrogen is going into the page. Because all these are trigonal planar, because they all have 3 bonds that are either trigonal planar or linear, so they're all in the same plane of the page. There's a hydrogen coming back at you. That hydrogen with the fully shaded in wedge is coming at you, and the hydrogen with the dashed wedge is coming into the page. So it's kind of just a convenient way of geometric representation of the molecule. Does that make sense? Okay, cool. So did I have more on this? No. So we're going to go back to the slides. Okay, so review of stability. This slide is literally copy and pasted from my last stream, except for the last part. So potential energy exists as a result of an object having a force on it, like something sitting above the Earth. There's a gravitational force acting on it, so there's a potential energy in that gravitational interaction. Or if you have a negatively charged and positive charge, or negative charge, positive charge, regardless, those combinations are either going to repel or attract each other. And for that to happen, there must be a force in between them. So if there's a force, there's a potential energy between them. And objects minimize their potential energy by turning it into kinetic energy, means moving to a position where it has less potential energy. So in the example of two positively charged things, when two positively charged things are far apart, they exert a different force on them. So intuitively, if you have two positively charged molecules or atoms even next to each other, are they repelling each other more when they're close apart or far apart? Yeah, so when they're closer together, there's more force, so there's more energy between them. And when they move away from each other, the force weakens, so the potential energy becomes lesser and lesser and lesser and approaches zero. So as they move away from each other, once they're an infinite distance away from each other, they have zero potential energy. So that's them minimizing their potential energy by moving, and by moving, they move apart from each other. And an object, by logic, is in its most stable state whenever it's in its minimum potential energy state. So I have a molecule, or an example would be like dropping an object to the ground. If I have something above the ground and I drop it, initially there's a force of gravity between the object that I'm about to drop and the ground. And as it approaches the ground, the potential energy approaches zero, because the potential energy is proportional to that height. So as the height decreases, the potential energy decreases. And it decreases the potential energy by moving to a place with less potential energy. And that place with less potential energy is the surface of the Earth, where that potential energy is zero, depending on your frame of reference. And that does that by moving towards the ground. And when it moves, it has kinetic energy. And then when it drops and hits the ground, you're probably thinking, well, it has zero potential energy and zero kinetic energy. So how did it get that? How did it lose its energy? If you think about it, when you drop something, it makes sound. And a sound is a wave, and a wave carries energy. So the energy is still there. It's just in terms of sound. And if you drop it hard enough, it'll produce light too. And by light, I mean like fire. But you'd have to drop it from a pretty far height and have to have a lot of mass. So the example here is 1,2-cyclohexane diol. Cis and trans isomers, the cis meaning the alcohol groups, not the alcohol group. Well, it is alcohol groups, but I'm using too much organic nomenclature right now. The OH, the hydroxide on the end, in the cis molecule, they're pointing in the same direction. So when we have this molecule, that means on the cis side, which is the left side, the two molecules are pointing in the same direction. They're both pointing out of the page. But on the right side, one OH is pointing out of the page and one is pointing into the page, and that's a trans isomer. So when we look at this molecule, which molecule is bigger, guys? A hydrogen or a hydroxide? And the hydroxide being the OH. Yeah, the OH is bigger. So the OH is, if the OH is bigger, that means that the OH groups, when they're pointing in the same direction, it's less stable. Because if they're big, think about it like having like two tether balls that are swinging on strings right next to each other. If they're big enough, they're going to hit each other. And that hit is a result of energy being released. So there's more potential energy in the interaction. That's why if you're moving things faster and you hit them on each other, and if they bounce off further, that means that they were moving faster after the collision to begin with, which means before the collision they had more potential energy. So in the same case here, they're just too close to each other. So the trans isomer in this case, where the OH parts of the molecule are pointing in opposite directions, it's more stable because the bigger groups are far away from each other. I have an example here actually. So this is 1,2-ethane or ethene diol. I'll make this ethane actually. That's probably going to be a better move because now they can rotate. I am doing construction. So one last addition. So this right here is 1,2-ethane diol. So there's rotation around this bond right here. There's free rotation around any sigma bond. That's also a detail that I forgot to mention. A pi bond, the molecule is rigid. Sigma bond, the molecule can rotate around like this. So here's two OH groups. Here's an O and here's an H. So this molecule, when it's in this state, these will rotate. And when they rotate, you see these hydrogens are hitting each other. But when it rotates down like this, there's no way this hydrogen is going to hit one of these things. And these are also, the OH are the bigger than these hydrogens off the side right here. So the interaction right here is unstable because you minimize the potential energy between two like charged things, like these two oxygens right here, by maximizing the distance between them. That's the same thing that I was talking about. If you have two charged particles that are the same charge, their potential energy is zero at an infinite distance. So these will maximize by spinning like this, moving from this state to a lesser potential energy state. And the distance is now maximized between the two oxygens. So this is a more stable state than this. Does that make sense? Any questions at all? All right, I'll take that as a good thing that there's no questions being asked. Slow me down if you ever need to, by the way. So how else do molecules stabilize? Molecules stabilize by resonance. And resonance is literally just the moving of electrons. The blue arrows meaning where the electrons go, which is a very smooth transition to the next part of the stream. So the next part of the stream is resonance. And resonance is when electrons move around on a molecule. This stabilizes the molecule because it lowers the average formal charge. And what is formal charge? It's just the number of available valence electrons minus the number of lone electrons on the atom minus the number of bonds on the atom. So if we think of something like nitrate, does anyone know the charge of nitrate off the top of their head? I wouldn't expect you to have it on the top of your head right now, but I would expect you to have it by the end of the year. Yeah, I think it's -2, right? Nitrate. Yeah, it's -2. No, it's -1. Yeah, nitrate is. I think you guys were confusing because I developed a Southern accent while living in South Carolina. No, they both have -1 charges. Okay. Nitrate has a -1 charge, but nitrate is 3 atoms that make up one molecule. And charge isn't like spread out, right? Charge is a discrete thing. So that charge has to lie on one of the atoms in that molecule. It can't be spread out across the entire molecule. So it has to be on one of the molecules. And formal charge is what tells you where on that molecule it is. So for example, we have, so the formal charge is literally just the number of valence electrons. So for example, for oxygen, that's 6. For nitrate, for nitrogen, that's 5. For carbon, it's 4. Minus the number of lone electrons on the atom, minus the number of bonds on the atom. So where where does the formal charge lie in ammonium and carbonate? So you can very clearly see the plus sign on the nitrogen in the ammonium ion. And the reason why is because nitrogen itself has 5 available valence electrons. There's 4 bonds in the molecule, and there's 0 lone pairs. So according to that formula on the previous slide, the formal charge on this nitrogen is going to be the number of valence electrons, which is 5, minus the lone electrons, which is 0, minus the number of bonds, which is 4. So the formal charge on the nitrogen is +1. Checking the hydrogens, there's only 1 available valence electron in hydrogen, and there's 1 bond. So 1 minus 1 is 0. Carbonate. So formal charge doesn't necessarily have to be solely on one atom. For something like ammonium that has only a +1 charge, or something like something with a different, or like a -1 charge, like nitrate, would have to be on one molecule. For carbonate, it's on both molecules. Drawing out the Lewis structure for carbonate, you can check the first oxygen. The first oxygen, or the top oxygen, has 6 total valence electrons available just by nature of oxygen. It has 6 lone pairs, or 6 lone electrons on it, and a single bond on it. So 6 minus 6 minus 1 is -1. Same goes for the oxygen on the bottom. So we're going to go over resonance. So we have O3 right here. And O3 is this structure, and it has a resonance structure, meaning the electrons are able to move around in the atom just by nature of the bonds. And those blue arrows mean the electrons go from where the arrow starts to the end of the arrow. So the formal charge on the middle oxygen in both cases, or we're going to look at the left case rather. The formal charge on the oxygen in the middle is 6 valence minus 2 bonds, it's minus 3 bonds, minus 2 lone pairs, so that's a +1. And the same case goes for the other oxygen, which is a -1. And do you guys see that the molecule essentially flips? Like it essentially just flips around on like a mirror. Yeah, so it's flipping around. So the oxygen is essentially mirrored. So the oxygen that had a +1 formal charge on the right side of the structure turns into a molecule that has a -1 formal charge. So it turns from a +1 to a negative. So the average formal charge is 0. And that's when the molecule is the most stable, when it has no charge. Or when the atom is most stable because it has no charge on it. Because if it has no charge, it obviously can't have those electric interactions with other charged things nearby it. So there's not going to be any potential energy between that and another charged particle because there's no charge on it. So that's the minimum state right there. It achieves 0 potential energy without being an infinite distance away. So there's 2 options for that atom. There's have a formal charge of 0, or be an infinite distance away from anything else that has a charge. And one of those is very plausible, more plausible than the other one. For 2 reasons. There's 2 reasons why the infinite distance thing is not plausible. The first reason is, infinite distance doesn't really exist. And second off is it's being bonded by a much stronger interaction with another oxygen. So there's 2 reasons why I can't move an infinite distance away. So we're going to go to the drawing board. So we're going to talk about drawing resonance structures. So I'm going to have to pull some stuff up on my phone to look up resonance structures that we can look at, and how to draw resonance structures, and the notation and all that. So I'm going to look up on my phone some resonance structures we can look at. For nitrate. So we're going to draw out nitrate. So if we look at a periodic table, we have nitrate being NO3 minus. This has 5 valence electrons. Nitrogen has 5 valence electrons. Oxygen has 6, so there's 3 of them, so there's 18 valence electrons. And then there's another +1 charge up here, so that's another random electron. So that's 6 plus 18 is 24 valence electrons in the molecule. So drawing out nitrogen, for nitrogen to even bond, or for there to even be a molecule, there has to be at least single bonds. Oxygen, oxygen, oxygen. So we're going to distribute some of the lone pairs here. So we'll just start by adding 1 lone pair on the oxygens each. So now we've used up 2, 4, 6, 8, 10, 12 of our available valence electrons. So let's try filling up these lone pairs again. So now we've used 2, 4, 6, 8, 10, 12, 14, 16, 18. So we have 6 more valence electrons. But as you can see, nitrogen hasn't filled an octet yet. So we need to double bond to this. And then do that, and do that. I'm going to move this down. This is inconvenient to have right here. Or I'll just cut this out of the picture. That's probably the better option. Okay, so does anyone see how the electrons can move around? Or how these can move around in the atom? Before I do it, can anyone see how they can move around, or how they're able to move around? Yeah, exactly. This lone pair can go here, but now this nitrogen has too many. It has too many bonds to it, so this lone pair has to go here. And we denote this having a -1 charge by drawing these brackets out with a -1 charge. So does that make sense where I got that from? Okay, so now we have, this is how we're drawing resonance structures, by the way, this double arrow to show that these structures are equivalent. Rather, I'll start drawing it again. So now with this new structure, we have an oxygen, nitrogen, oxygen, oxygen. So now we don't have this double bond anymore. We have 3 lone pairs on this top oxygen. And now there's a double bond with this oxygen and 2 lone pairs. And this still has 3 lone pairs. And then this gets probably should have drew this further away from the arrow. So now this has the same charge, -1. And does anyone see the third resonance structure we can draw? Here, I'll zoom out a little bit. Does anyone see the third resonance structure we can draw? I still have to draw arrows on this because I haven't drawn them yet to do a little demonstration with this. Yeah, just the same essentially structure like this. So the bond, those electrons move here to create a pi bond with the nitrogen. But now this lone pair, now this nitrogen is exceeding the octet, so it has to, the lone pairs have to move. And now you have nitrogen, oxygen, 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 and now this oxygen is a double bond with 2 lone pairs, 3 lone pairs on this one, and 3 lone pairs on this one. And that has a -1 charge. So Here's the caveat here. For AP, you do not need to draw these arrows, or you need to draw the double arrows, but you don't need to draw the arrows showing where the electrons are going. Really, my recommendation is to do it anyway, just because it really makes the whole thing makes more sense. You're not just drawing separate structures. It feels like it's the same structure going through transition stage, which is a little more accurate than before. So my recommendation is to do that. Draw these resonance arrows that show where the electrons are going and where they're coming from, because it'll make the whole drawing process make a lot more sense. Your teacher personally might see the arrows on your final answer and be like, oh, that's wrong. I never taught that. But in that case, just draw your final answer without the arrows, but in your work, draw the arrows out. And these arrows also become very important once you start, or if you start taking organic chemistry in college, or if you take it at a community college during high school, like my friend did, or your school offers it, or you learn organic chem as the last unit after the AP exam. Really any possibility. These electron arrows become very important. So we're going to talk about assigning formal charges to these. So when we're talking about the nitrogen here, right, there should be is there formal charges on these? So this is -5, -4. Okay, I see what's wrong. So what's the formal charge on this nitrogen, guys? If you remember the formula, it's number of valence electrons minus the number of lone electrons minus the number of bonds. That's formal charge. So what's the formal charge on the nitrogen here? You can throw a guess out there. Tough crowd tonight. All right. So for the nitrogen here, it has 5 valence electrons just by the periodic table trend. The number of lone electrons on it, there's no lone electrons on it, it's 0, and the number of bonds is 4. So this has a +1 positive formal charge, or we'll just put +1. How about these 2 oxygens right here? By the same process, what are those 2 oxygens, or the formal charge of these 2 oxygens on the bottom right here? They're both the same atom, essentially. So go ahead and, if you didn't answer the last one, try and answer the formal charge on those oxygens. Yeah, it's -1. 6 valence electrons minus 6 lone electrons minus 1 bond, which is -1. So I'm going to go ahead and get these lines off because it's going to be a little confusing. So that is -1, and that is -1. And what's the formal charge of the top oxygen? Yeah, there's no formal charge on the top oxygen. So these formal charges all add up to the total charge of the ion. You guys all see that? Awesome. So going through the same process again, this becomes a +1 formal charge, 0, not 0. This is -1. -1. And again with this, +1, 0, -1, -1. So what do you so let's talk about the average charge of the top one between these 2 structures. What's the average charge of the top oxygen? You don't have to make it a decimal. You can just leave it in fraction form. So the actual calculation is irrelevant, but seeing the number itself is very relevant. Yeah, so the average, we'll call this oxygen alpha. It's a fancy Greek letter. So the average charge is what this bar means for the alpha oxygen is -2/3. And that's also the same case for all of these. So going through the Greek alphabet again, because I like Greek letters, beta, the beta oxygen, the gamma oxygen. That's just how the Greek alphabet goes, alpha, beta, gamma. So the average, and this is also equal, I'm not going to write it out again. It's also equal to the average charge on the beta oxygen, which is also equal to the average charge on the gamma oxygen. So what about the average charge on the nitrogen? Yeah, the average charge on the nitrogen is just a +1. So there's two important things here. The resonance adds stabilizes things for two reasons. The first off is that this is the lowest possible way you could get the average formal charge to be closest to 0. This set of structures really makes it so the average formal charge on each of the molecules is close to 0. However, there's another takeaway here. How should I put this? The more electronegative part of the molecule is the one that bears the negative charge. And that should make some sense, at least by intuition, because electronegativity means it pulls in electrons, and if it pulls in electrons, it has a more partial negative charge. So in the most stable case, the more electronegative atom is the one that's bearing the negative charge. And you do see this here. When you're talking about oxygen, it's more electronegative. So it's bearing that negative charge, or most of that negative charge that molecule carries. Does that make sense, guys? Okay, cool. So resonance structure examples. We'll look up another example to do. Oh, this is all organic chemistry. That's not fun. What is all organic chemistry? You guys are not taking organic. Well, actually, that's probably because my that's my that's why I look up a lot, because I need a lot of help, because organic is hard. Okay, so we're gonna do nitrate now, or nitrite, NO2 negative. So drawing the structure out, nitrogen's in the middle, 2 bonds to oxygen. How many total electrons are in here? 5 plus 2 times 6 plus that extra charge. So that's 12 plus 6, which is equal to 18. So we'll fill up some lone pairs here. Now we've used 8. We'll do another set of lone pairs on each oxygen. Now we've used 2, 4, 6, 8, 10, 12. So now we have 6 more to use. And if you try structures, you have to put a double bond here, or put a lone pair there, double bond there, and then another pair of electrons right there. So we'll check that. That's 2, 4, 6, 8, 10, 12, 14, 16, 18. Awesome. So we're going to draw some resonance structures for this, where we have to put that this is a -1 charge. Okay, so How can the electrons move around here, guys? How do you think? How do you guys think the electrons can move around here? Yeah, exactly. So this goes here. Actually, this is a better way to talk about it in order. This goes there, but now this nitrogen has too many electrons, so this one gets pushed over here. And now we have oxygen with 3 lone pairs, singly bonded to a nitrogen, and then this oxygen now is a double bond, 2 lone pairs, and a lone pair on the nitrogen. With -1. So it's a -1 formal charge, or a -1 total charge. So the formal charge can only lie on one atom. And where do you think in the first structure that lies? So just wherever there's a non-zero formal charge on the molecule. So it's right here because there's 6 available valence electrons minus 6 pairs minus 1 bond, which equals -1. And by talking about the symmetry of the molecule, that means that there's also the formal charge right here. There's a lot of practice sheets to do this stuff on, but the only problem is chemistry is a new subject in Fiveable, so there's not a whole lot of resources on Fiveable, but you can find stuff online. So we're gonna go back to the slides now. And talk about applications of this to acids and bases. So an acid is just, what exactly you think an acidic thing is. It's sour. It's generally seen as dangerous, but strong acids mean an acid that dissociates a lot when you put it in water, meaning the actual molecule splits up a lot in water, and they produce weak bases in the product. So stronger acids are not stable because strength of acid is the strength of the acid is how likely it will donate a hydrogen ion, turning it into a more stable compound. So stronger acids occur with stable bases. So if a base has resonance structures, then the acid is stronger than a base without resonance structures. And the reason why is because if the conjugate base on the other side, the HB, is or has resonance structures, it's more stable. So the lower potential energy state occurs at the structure with resonance because resonance stabilizes molecules. So when we talk about example, we'll talk about phenol. Phenol reacting with hydroxide makes this reaction. It makes phenoxide and water. So the reason why the arrow goes from there is because the arrow goes from the hydroxide to the hydrogen, even though you normally think of it the other way around. It's because it's the way the electrons travel, not the way the atom travels. Phenol is a relatively strong base compared to similarly structured molecules because its conjugate base, the phenoxide, has resonance. And this is proved with data. So the left is phenol and the right is cyclohexanol. You can see that those structures are very similar. There shouldn't be a lot of difference in their strengths. However, there's a lot of difference in their strength. It's a big difference. And you may think it's only like 6, but that's logarithmic. So that means that there's more like a difference of 10 to the 6th, which is 1,000,000. So there is a very big difference in their relative strength. We're going to talk about that. And I'm going to show you why it's stronger. So the phenoxide resonance and the cyclohexane oxide. So we're going to go back to the drawing board for these last 5 minutes. Don't worry if this is kind of going over your head because you don't have to learn acid and bases yet. I did not mean to reshare that. Technology's hard. Application window. Okay, so I'll expand the canvas and make this a white background. That's a great idea. Okay, so when we talk about the resonance in this phenoxide, I'm not going to draw the resonance structures. I'll just draw the different steps. So what starts the resonance is the lone pair moves down here and creates a double bond with that carbon. But now this carbon has 5 bonds, and that's no good. So now the double bond moves down here. But wait, now this carbon has 5 bonds. So now this has to move. So this moves over here. But wait, now this has 5 bonds. So now this has 5 bonds. So this moves here. So this is step 1. This is step 2, step 3, step 4. Now when we look at cyclohexanol in the example that I gave before, which was, for example, this was the the notation for the other one. Don't worry if you don't get the line structure. I'm literally just giving an introduction here, trying to show you that this stuff kind of is important. So when we have cyclohexanol, we have 6 carbons bonded in a hexagon. And I'm not going to draw on the hydrogens just because they're not very important to this discussion, but know that there are hydrogens in these carbons to make them fully fill the octet. And there's an alcohol here, or a OH here, a hydroxide here. And when this reacts with hydroxide, again, I'm not drawing the lone pairs just because they're not really relevant right now. The reaction is simply, this will make it more clear actually. Hold on. There's a bond between this oxygen and this hydrogen here. So what happens is the mechanism here is this goes to the hydrogen, so this bond breaks, and then this attacks the hydrogen and forms some products. And the products it forms are, and initially this has the minus formal charge. It forms cyclohexane oxide, which looks like this. God, if you hear that banging, it's because my people in my hall are really annoying sometimes, really loud, but I'm a college freshman, so of course they're loud. So now this has an oxygen here with a formal charge, and it also makes water. And as you can see, there's no resonance that can be drawn here on this this cyclohexanol oxide right here, or this cyclohexane oxide. There's no resonance, and because of that, there is a very big difference in their strengths, and the strengths between phenol and cyclohexanol, even though the structures are very similar. This would be cyclohexanol, and this is the phenol right here. So between cyclohexanol and phenol, their structures are very similar, but because there's resonance in that conjugate base, if the conjugate base is stable, then the acid is unstable, which means that it's stronger. Because it's strong just means it's more likely to break apart. And breaking apart is one of the methods that something gets to lowering its potential energy. So in that case, the cyclohexanol is less strong. It's weaker because it's more stable than the phenol. I'd ask, does that make sense? But it probably doesn't, because acid base is kind of a complicated subject, and I literally just went over this for like 5 minutes. But it's more so an introduction to what you're going to be learning soon. And one thing I forgot to talk about was bond order. So when we have stuff right here, the bond order would just be the number of bonds in any given molecule, or the number of bonds. So for example, something like cyanide, which has a structure like that, has a bond order of 3. But in this case, the bond order gets lowered by these, because the bond order would just be, for example, the bond order in this bond right here is 1. In this bond right here, I'm going to put purple on that. And then the bond order in this one on that same molecule is 2, and this one is 1. So the bond order is the average of these, which is 2 plus 1 plus 1 divided by 3, which is 4/3. So when you're talking about bond order and asking bond order about something, just draw the structure, and if there's resonance, then there's a little different procedure for drawing bond order. But in the case of cyanide, there's no resonance, so this bond order is simply 3. But in this case, you have to check all the resonance structures and then average them out to find the bond order. So that's all I have for you. Any questions at all? Any questions, guys? All right, I'll take that as a no. So if you want to ask me further questions or want to ask me questions about your homework or something like that, put my Instagram in the chat. You can shoot me a DM and I'll answer it as soon as I can or as soon as I see it. So have a good night, guys. Take it easy.